There is a problem at the heart of physics that most people have never heard of, and it is one of the most disturbing questions science has ever produced. The universe, as best as we can measure, contains slightly more matter than antimatter. Not dramatically more, not twice as much or 10 times as much, just barely more. Roughly one extra particle of matter for every billion particle-antiparticle pairs that existed in the early universe. Every atom in your body, every planet, every star, every galaxy, all of it descended from that tiny excess. If the universe had been perfectly symmetric, matter and antimatter would have annihilated each other completely in the first fraction of a second after the Big Bang, and the universe would contain nothing but radiation, no stars, no planets, no chemistry, no life, just light, cooling, and thinning forever in an empty cosmos. The fact that we exist means the symmetry was broken. Slightly, briefly, but enough, and we do not fully understand why. The technical name for this asymmetry is baryogenesis, the process by which the universe came to contain more baryons than antibaryons in the early moments after the Big Bang. The laws of physics require three conditions to produce such an asymmetry, identified by Soviet physicist Andrei Sakharov in 1967, baryon number violation, meaning some process must be capable of changing the total number of baryons, violation of charge conjugation symmetry and charge parity symmetry, meaning the laws of physics must treat matter and antimatter differently in at least some small way, and departure from thermal equilibrium, meaning the processes must happen in a universe that is not perfectly symmetric in its thermodynamic state. All three of these conditions are met, at least partially, by the physics we know. The weak nuclear force does violate CP symmetry. This has been measured directly in the decays of certain particles called kaons and B mesons. But the amount of CP violation observed in the standard model of particle physics is by several orders of magnitude too small to produce the observed matter-antimatter asymmetry. The standard model cannot explain why we exist. Something beyond it must be responsible. Finding the source of CP violation large enough to account for baryogenesis is one of the primary motivations for building ever larger particle accelerators and conducting ever more precise measurements of particle decays. We are searching essentially for the reason the universe is not empty. Antimatter itself is real, detectable, and produced routinely both in nature and in laboratories. When a sufficiently energetic gamma-ray photon passes near an atomic nucleus, it can spontaneously convert into an electron and its antimatter counterpart, a positron, a particle with the same mass as an electron but opposite charge. This is pair production, a direct conversion of energy into matter and antimatter in equal amounts, just as Einstein's equation predicts. Positrons are also produced by certain radioactive decays and by cosmic ray interactions in the upper atmosphere. The antimatter particles produced in these processes survive for only tiny fractions of a second before encountering ordinary matter particles and annihilating, converting back to gamma rays in a flash of energy. PET scanners, positron emission tomography machines used in medical imaging, work by injecting a patient with a glucose molecule tagged with a positron-emitting isotope, typically fluorine-18. The isotope decays, producing positrons that immediately annihilate with electrons in nearby tissue, producing pairs of gamma rays traveling in precisely opposite directions. Detectors surrounding the patient catch the coincident gamma ray pairs and reconstruct the three-dimensional location of the annihilation events, producing a map of metabolic activity in the body. Every PT scan is a practical application of matter-antimatter annihilation, a process operating at the boundary of quantum field theory and medical diagnostics in hospitals around the world every day. The solar wind, the continuous stream of charged particles flowing outward from the sun, is something most people know exists abstractly but rarely think about as a physical force shaping the solar system. It is not a uniform breeze. It is a structured, variable outflow ranging from slow wind, about 300 to 400 kilometers per second, denser, emerging from the sun's equatorial regions associated with helmet streamers in the corona, to fast wind, exceeding 700 kilometers per second, thinner and more uniform, flowing out from coronal holes where the sun's magnetic field lines open directly into interplanetary space, rather than looping back to the surface. When fast wind runs into slow wind ahead of it, the interaction produces a compressed region called a corotating interaction region, a structure that rotates with the sun and sweeps past Earth roughly every 27 days. These interactions can drive moderate geomagnetic storms. Far more dramatic are coronal mass ejections, CMEs, Sudden eruptions of magnetized plasma from the sun that can release up to 10 billion tons of solar material into space at speeds ranging from a few hundred to a few thousand kilometers per second. A fast CME, launched from the sun, reaches Earth in as little as 15 to 18 hours. When it arrives, the interplanetary magnetic field embedded in the CME interacts with Earth's magnetosphere. If the CME's magnetic field is oriented southward, opposite to Earth's northward magnetic field at the equatorial boundary, reconnection occurs, and enormous amounts of energy are transferred into the magnetosphere. The result can be a severe geomagnetic storm, induced electrical currents in the ground that can overwhelm power transformers, disrupted GPS and radio communications, elevated radiation doses for astronauts and high-altitude airline passengers, and aurora visible at latitudes far from the poles. In May 2024, a series of powerful CMEs struck Earth in succession, producing the strongest geomagnetic storm in about 2 decades and generating visible aurora as far south as Florida and Texas, as far as Mexico, and even parts of the Caribbean. Social media filled overnight with photographs that looked, to people who had never seen them, like something the sky had never done before. The sky does this constantly. Most of the time, we are not paying attention. The Parker Solar Probe, launched in 2018 and named for astrophysicist Eugene Parker, who first theoretically described the solar wind in 1958, has been making increasingly close passes of the sun, swooping to within about 7 million kilometers of the solar surface at its closest approach, closer than any previous spacecraft, inside the orbit of Mercury, well within the sun's outer atmosphere, the corona. At that distance, the probe is moving at roughly 700,000 kilometers per hour, making it the fastest human-made object ever built. And it is doing something that seemed paradoxical for decades, entering a region that is hotter than the surface of the sun. The surface of the sun, the photosphere, is about 5,500 degrees Celsius. The corona, which extends millions of kilometers above the surface, reaches temperatures of several million degrees. Why the corona is so much hotter than the surface it sits above, the so-called coronal heating problem, has been debated since the 1940s and is one of the oldest unsolved problems in solar physics. Parker has found evidence that small, impulsive heating events called switchbacks, rapid reversals in the direction of the solar magnetic field that produce localized bursts of heating, may contribute. It has also found that the solar wind reaches its full speed closer to the sun than expected. The story is still being assembled, but Parker is writing chapters of it with every close pass. The aurora, the northern and southern lights, are among the most beautiful phenomena in nature, and they are entirely a consequence of the same physics we have been discussing. Charged particles from the solar wind and from geomagnetic storms are funneled by Earth's magnetic field into the polar regions, where they collide with molecules in the upper atmosphere and excite them to higher energy states. As those molecules relax, they emit light, the specific colors determined by which molecules are involved and at what altitude. Oxygen at high altitudes, above about 200 kilometers, produces rare red aurora. Oxygen at lower altitudes, around 100 kilometers, produces the most common green aurora. Nitrogen produces blue and purple hues. The curtains and rays of aurora visible from the ground are shaped by the structure of the magnetic field lines along which the particles travel. The aurora trace the geometry of the magnetosphere painted on the sky in light. The aurora are not unique to Earth. Jupiter has aurora, produced by its own powerful magnetosphere interacting with the plasma torus shed by Io's volcanoes. Saturn has aurora. Uranus and Neptune have aurora. Even Ganymede, Jupiter's moon with its own magnetosphere embedded in Jupiter's much larger one, has localized aurora near its poles. The magnetosphere of Earth is a structure of extraordinary complexity and importance. It is the region of space dominated by Earth's magnetic field, extending roughly 60,000 kilometers toward the sun and stretching out millions of kilometers in the downwind direction into a long magnetotail. The magnetosphere deflects the solar wind around Earth, protecting the surface from direct exposure to solar wind particles and significantly reducing the cosmic ray flux at the surface. Without a magnetosphere, Earth would be a different world. The solar wind would strip the upper atmosphere over geological timescales, much as Mars lost most of its atmosphere after its core cooled, its dynamo shut down, and its magnetic field faded roughly 4 billion years ago. Venus has no significant magnetic field and is also losing atmospheric particles to the solar wind, though slowly, and its thick atmosphere provides enough pressure that the loss has not been catastrophic over the planet's history. Earth's magnetic field is generated by convective motions of liquid iron in the outer core, a self-sustaining electromagnetic dynamo that has maintained the field, with fluctuations and reversals, for at least 3.5 billion years. The field has reversed its polarity hundreds of times over Earth's history, with reversals taking thousands of years during which the field weakens dramatically before recovering with opposite polarity. The last reversal, the Bruni's-Matiyama reversal, occurred about 780,000 years ago. We are not currently in a reversal, but the field has been weakening at about 5% per century over the past 2 centuries, which some have taken as a sign that a reversal may be approaching. Whether it is or not, we cannot predict reversals reliably, and a prolonged weakening of the field would significantly increase the radiation environment at the surface and the vulnerability of satellite infrastructure. Wolf-Rayet stars are some of the most spectacular and extreme objects in the stellar zoo. Massive stars, many times the mass of our Sun, that have shed or are actively shedding their outer hydrogen envelopes through powerful stellar winds, exposing the hot, dense interior layers where helium, carbon, nitrogen, or oxygen burning is proceeding. The surface temperatures of Wolf-Rayet stars reach 25,000 to 50,000 Kelvin or more, making them among the hottest stars known, and their luminosities are hundreds of thousands to millions of times that of the Sun. Their spectra are unmistakable, broad, strong emission lines of helium and heavy elements, broadened by Doppler shifts from the fast-moving wind that is streaming away from the star's surface at up to a few thousand kilometers per second. A Wolf-Rayet star losing mass in its wind sheds an amount equivalent to an Earth mass every few years. Over the star's relatively short remaining lifetime, Wolf-Rayet stars are massive and therefore short-lived, burning for only a few 100,000 years in this phase. It may shed several solar masses of material. This material forms spectacular shells and rings of glowing gas around the star, illuminated by its ultraviolet radiation, like a stellar nebula being actively blown into existence. The fate of most Wolf-Rayet stars is a violent one. A supernova, possibly a hypernova if the core collapse is sufficiently energetic, possibly accompanied by a long gamma-ray burst, if the star retains enough angular momentum to form a relativistic jet. The progenitor of many long gamma-ray bursts is thought to be a Wolf-Rayet star, a stripped, rapidly rotating massive stellar core collapsing directly to a black hole. WR-104, a Wolf-Rayet star about 8,000 light-years from Earth, has attracted attention because its rotation axis appears to be roughly aligned with the direction toward Earth. If WR-104 produces a gamma-ray burst when it eventually explodes, and not all Wolf-Rayet stars do, and if the burst beam is indeed pointed toward Earth, the consequences would be significant. But the uncertainties in both the alignment and the star's proximity to explosion are large enough that astronomers do not currently consider WR-104 a meaningful near-term threat. Binary star systems, systems where 2 stars orbit their common center of mass, are extraordinarily common. Roughly half of all Sun-like stars are in binary or higher-order multiple systems, and for more massive stars the fraction is even higher. The variety of binary star phenomena is enormous. Close binaries with periods of hours or days can transfer mass from one star to the other as they evolve, producing a rich menagerie of exotic objects, cataclysmic variables, where a white dwarf accretes material from a companion and periodically erupts in thermonuclear outbursts called novae; symbiotic binaries, where a white dwarf accretes from the wind of a giant companion; and X-ray binaries, where a neutron star or black hole accretes material from a companion star and the infalling material heats to temperatures of millions of degrees, emitting X-rays. The first black hole ever identified, Cygnus X1, was detected not by observing the black hole itself, but by observing its X-ray binary companion, a supergiant star called HDE 226868, which is losing mass in a stellar wind, some of which is captured by the gravitational field of an unseen companion whose mass calculations from the orbital dynamics exceed the maximum possible mass of a neutron star. Cygnus X1 was at the center of a famous bet between Stephen Hawking and Kip Thorne in 1974. Hawking bet against it being a black hole, as a kind of insurance policy, he said, against a career spent on a subject that turned out not to exist. He conceded the bet in 1990 when the evidence had become compelling. In 2021, refined measurements placed the mass of the Cygnus X1 black hole at 21 solar masses, and confirmed that it is a stellar mass black hole rotating at more than 95% of the maximum rate allowed by general relativity, what is called a near-extremal Kerr black hole, spinning so fast that its ergosphere, the region outside the event horizon where space itself is dragged around in the direction of rotation, extends significantly beyond the horizon. The ergosphere of a rotating black hole is one of the most conceptually strange features of general relativity's predictions for these objects. Inside the ergosphere, the dragging of spacetime by the black hole's rotation is so extreme that nothing, not even light, can remain stationary relative to distant observers. Everything inside the ergosphere is forced to co-rotate with the black hole, even if it is not inside the event horizon and could theoretically still escape. The Penrose process, proposed by Roger Penrose in 1969, describes a mechanism by which energy can actually be extracted from this rotation. If a particle enters the ergosphere and splits into two, with one part falling into the black hole and the other escaping, the escaping part can emerge with more energy than the original particle brought in, extracting rotational energy from the black hole. The black hole slows slightly. Over time, a rapidly rotating black hole can lose a significant fraction of its mass energy through this process. The Blandford's-Najek mechanism, a version of this idea involving magnetic fields threading the ergosphere, is believed to be responsible for the relativistic jets produced by some black holes, streams of plasma and radiation ejected from the poles at nearly the speed of light, powered by the rotational energy of the spinning black hole, producing some of the most energetic continuous sources of radiation in the universe. The concept of a tidal disruption event. What happens when a star wanders too close to a supermassive black hole and is torn apart, is one of the most spectacular and observationally accessible phenomena in high-energy astrophysics. A star approaching a supermassive black hole within a critical distance called the tidal radius, which depends on the masses and sizes of both objects, experiences a difference in gravitational force between its near and far side that exceeds its own self-gravity, and it is stretched and ultimately disrupted, shredded into streams of gas that loop around the black hole and feed into an accretion disk. The sudden formation of this accretion disk from a previously quiescent black hole produces a luminous flare, a tidal disruption event, or TDE, that brightens over days to weeks and fades over months to years. TDEs have been observed in ultraviolet, optical, X-ray, and radio wavelengths, and they provide a unique opportunity to watch a previously inactive black hole suddenly switch on. Some TDEs produce relativistic jets, narrow beams of radio-emitting plasma, launched at nearly the speed of light, while others appear to produce only thermal radiation from the forming accretion disk. The exact conditions that determine whether a jet forms are not well understood, making TDEs a rich topic of current research. The most distant TDE yet observed was detected by JWST in 2023, at a redshift corresponding to the universe being only about 1/6 its current age. Neutrinos, subatomic particles produced in enormous quantities by nuclear reactions in stars and supernovae, as well as by certain radioactive decays, are among the most ghostly objects in the known universe. They have mass, though extraordinarily small. The upper limit on the sum of all three neutrino masses from cosmological constraints is less than 1/10 of an electron volt, compared to the electron's mass of about 511,000 electron volts. They interact with ordinary matter only through the weak nuclear force and gravity, making them extraordinarily difficult to detect. About 100 billion solar neutrinos pass through your thumbnail every second. In your entire lifetime, a handful of them will interact with atoms in your body. The others pass through unimpeded, through the Earth, through the Sun, through light years of dense matter, barely noticing it is there. The solar neutrino problem was one of the great puzzles of late 20th century physics. Calculations of the rate of nuclear fusion in the Sun predicted a specific flux of neutrinos at Earth. When experiments were built to detect them, deep underground, to shield against cosmic ray backgrounds, using large tanks of chlorine or water as targets, the detected flux was only about 1/3 to 1/2 of the predicted value. For decades, the discrepancy was considered either a sign that our models of the Sun's interior were wrong, or a sign that something was wrong with particle physics. The resolution, confirmed by the Sudbury Neutrino Observatory in Canada in 2001 and recognized with the Nobel Prize in Physics in 2015 for Art MacDonald and Takaki Kajita, was that neutrinos oscillate. They change flavor as they travel, shifting between the three known types, electron neutrinos, muon neutrinos, and tau neutrinos over distance. The solar neutrinos produced in the Sun's core are electron neutrinos, but by the time they reach Earth, a significant fraction have oscillated into muon and tau neutrinos, which the earlier detectors were not sensitive to. Neutrino oscillation requires neutrinos to have non-zero mass, which was not predicted by the original standard model of particle physics. This was the first definitive evidence that the standard model was incomplete, a crack in the theoretical framework that has motivated a generation of theoretical work. The IceCube Neutrino Observatory at the South Pole is the largest neutrino detector ever built, consisting of over 5,000 optical sensors embedded in a cubic kilometer of Antarctic ice at depths between 1.5 and 2.5 kilometers. The ice is extraordinarily transparent, among the clearest natural materials on Earth at the relevant depths, allowing the sensors to detect the faint flashes of blue light called Cherenkov radiation produced when a high-energy neutrino from space occasionally interacts with the ice and produces a secondary particle traveling faster than light moves through ice. IceCube detects neutrinos with energies up to quadrillions of electron volts, far exceeding anything produced in particle accelerators, arriving from all directions. In 2013, IceCube announced the detection of the first high-energy astrophysical neutrinos, naming individual events after scientists including Bert and Ernie from Sesame Street. Since then, sources have been identified. In 2022, IceCube definitively identified the galaxy NGC 1068, also known as Messier 77, a nearby Seyfert galaxy with an active nucleus, as a high-energy neutrino source. In 2023, the first detection of neutrinos from the Milky Way's galactic plane was announced. Diffuse neutrino emission from the disk of our own galaxy produced by cosmic ray interactions with interstellar gas. Neutrino astronomy is now a real science, opening a completely new window on the high-energy universe. Blazars are among the most luminous and variable objects in the sky, a subtype of active galactic nucleus in which the relativistic jet produced by the central supermassive black hole happens to point almost directly toward Earth. Because we are looking almost straight down the barrel of the jet, the observed luminosity is amplified by relativistic beaming, the same effect that makes the headlights of a fast-moving car appear brighter than the taillights, by factors of hundreds or thousands. A blazar can vary in brightness by a factor of 10 or more in a single day, as irregularities in the jet pass through the relativistically beaming zone. The most distant blazars are detectable at cosmological distances, their jets carrying enough energy to outshine an entire galaxy of stars in a single wavelength band. Blazars are thought to be among the primary sources of the highest energy cosmic rays reaching Earth, as well as contributing to the high-energy neutrino background detected by IceCube. In 2017, a neutrino detected by IceCube was traced back to a direction consistent with a blazar designated TXS 0506+056, which was simultaneously flaring in gamma rays, the first multi-messenger detection involving a neutrino and a specific astrophysical source other than a supernova. The Veil Nebula, visible in the constellation Cygnus, is one of the most visually spectacular supernova remnants in the sky. It is the expanding shell of gas from a supernova that occurred about 10,000 to 20,000 years ago, at a distance of about 2,100 light-years. The original star, probably between 15 and 40 times the mass of our Sun, exploded and sent its outer layers expanding outward at thousands of kilometers per second. Today, after thousands of years of expansion, the shell has slowed and spread into fine, wispy filaments of glowing gas, oxygen, hydrogen, sulfur, that span about 110 light-years across and are visible through even a modest telescope as delicate, lace-like structures. Hubble images of the Veil Nebula show individual filaments in extraordinary detail, the gas lit by the shock front where the expanding remnant plows into the surrounding interstellar medium, compressing and heating it to temperatures of 30,000 Kelvin or more. The central neutron star from the original explosion has never been definitively identified. It may have received a kick velocity from the asymmetric explosion and left the vicinity entirely, or it may be a dim pulsar not yet detected. Cassiopeia A is a younger and more energetic supernova remnant, the remains of a massive star that exploded roughly 340 years ago. Based on the expansion rate of the shell, though no historical record of the explosion itself has been found, suggesting the original supernova may have been obscured by interstellar dust or may have been intrinsically faint for its distance of about 11,000 light-years. Cassiopeia A is the brightest radio source in the sky beyond the solar system, and it has been one of the most studied objects in high-energy astrophysics since its discovery in 1947. Chandra X-ray Observatory images of Cassiopeia A show a complex, asymmetric shell of shock-heated gas at temperatures of tens of millions of Kelvin, with a central compact source, the neutron star formed in the explosion. In 2013, astronomers reported evidence that the surface of the Cassiopeia A neutron star had cooled significantly in just 10 years of observation, a rate consistent with the formation of a neutron superfluid in the core as the star cools through a process called enhanced cooling. This was the first observational evidence of superfluidity in a neutron star interior, a quantum mechanical state in which neutrons flow without viscosity, a property with significant implications for neutron star dynamics and pulsar behavior. The Large Magellanic Cloud has its own intense star-forming region called 30 Doradus, also known as the Tarantula Nebula, the largest and most active star-forming region in the local group of galaxies. At its heart is a cluster of hot, massive stars called R136, which contains some of the most massive stars known to exist. R136A1 was long considered the most massive star ever confirmed, with estimates reaching up to perhaps 260 solar masses, far exceeding the theoretical upper mass limit for stable stars that had been calculated at about 150 solar masses, a limit based on the balance between radiation pressure and gravity that should prevent stars from accreting more mass beyond this point. Stars like R136A1 challenge this limit and are thought to have formed through the merger of multiple massive stars in the dense cluster, effectively bypassing the limit by combining already formed stars rather than accreting from scratch. The entire Tarantula Nebula region, roughly 1,000 light-years across, is so actively forming stars that if it were as close to Earth as the Orion Nebula, about 1,300 light-years, it would cast visible shadows on the ground at night. The Orion Nebula itself, visible to the naked eye as the middle star of Orion's sword, is actually a stellar nursery about 40 light-years across, located about 1,300 light-years from Earth, where hundreds of young stars are actively forming and illuminating the surrounding gas with their ultraviolet radiation. The nebula is part of a much larger molecular cloud complex, the Orion Molecular Cloud, which spans several hundred light-years and contains enough gas to form thousands of stars. Within the Orion Nebula, Hubble and JWST have resolved objects called proplids, protoplanetary disks, young solar systems in the making, seen edge-on or face-on as dark silhouettes against the bright nebular background. These disks are being photoevaporated by the ultraviolet radiation from the massive trapezium stars at the heart of the nebula, gradually stripped away over tens of thousands of years. Whether the planets forming inside them can complete their assembly before the disk is destroyed depends on a race between planet formation timescales and photoevaporation rates. In some cases, the disk is clearly losing the race. In others, planets may already be forming inside the surviving inner disk regions, shielded by their own mass. The Orion Nebula is in effect a laboratory where we can watch the planet formation process in real time, at every stage, across hundreds of systems at once. T-Tauri stars, young pre-main sequence stars still contracting toward the hydrogen burning that will define their main sequence life, are the precursors of sun-like stars, and are common in star-forming regions like Orion. They are surrounded by the protoplanetary disks from which planetary systems assemble, and they are extraordinarily active, producing strong ultraviolet and X-ray flares, driving bipolar jets of gas from their poles, and accreting material from their disks through magnetic field lines that funnel in falling gas onto the stellar surface at specific accretion spots. The variability of T-Tauri stars. They brighten and dim irregularly as accretion rates fluctuate and as disk material occults them, was recognized and puzzled over for decades before the physical picture became clear. Some T-Tauri stars are surrounded by warped or misaligned disks, produced by the gravitational influence of a companion star in a binary system, that produce complex and distinctive variability patterns as the warp precesses and periodically blocks the starlight. Studying T-Tauri stars and their disks gives us a window into the conditions of our own solar system about 4.5 billion years ago. The chaos of accretion and jet activity, the energetic young sun, the protoplanetary disk gradually clearing as the planets assembled. The asteroid belt between Mars and Jupiter contains a few 100,000 known asteroids larger than a kilometer and millions of smaller bodies. But the total mass of the belt is surprisingly small, less than 4% the mass of the Moon, and far less than models of solar system formation predict for a region that should have accumulated a full-sized planet. The reason for this mass deficit is Jupiter, its gravitational influence, especially at specific orbital resonances, locations where the orbital period of an asteroid is a simple fraction of Jupiter's orbital period, stirred up the belt's population, increasing collision velocities to the point where collisions between bodies produce destruction rather than accretion, and gravitationally ejected much of the belt's original mass. The asteroids we see today are not the leftovers of a planet that failed to form from too little material. They are the fragments of a planet that was prevented from forming by too much gravitational disruption. The distribution of asteroid families within the belt reflects its violent history. Many asteroids cluster together in what are called collisional families, groups of bodies with similar orbital elements and similar compositions, descending from the breakup of a single larger parent body in an ancient collision. The Veritas family, for instance, traces back to the collision of a large body about 8 million years ago. A collision we can date because the family members' orbits have diverged at a predictable rate from the point of breakup. Within families, the Yarkovsky effect, a subtle non-gravitational force produced by the asymmetric thermal emission of heat from a rotating asteroid, where the sunlit morning side emits less heat than the afternoon side, creating a tiny but persistent thrust, gradually moves individual asteroids through the belt over millions of years, slowly changing their orbital elements. The Yarkovsky effect is small but cumulative, and over long timescales it is responsible for delivering asteroids from the main belt into Jupiter-crossing orbits, from which they eventually become near-Earth asteroids or are ejected from the solar system. Near-Earth asteroids that cross Earth's orbit are monitored obsessively by a global network of survey telescopes, and the vast majority of large ones, larger than a kilometer, have been found and their orbits determined to be non-threatening for at least the next century. But smaller objects in the 100-meter to kilometer range remain incompletely catalogued, and it is in this size range that the Chelyabinsk scale to city-killer range of impacts fall. The discovery rate of near-Earth objects has accelerated dramatically with modern survey telescopes like Pan-STARRS and Catalina Sky Survey, and the Vera Rubin Observatory will find thousands more. The goal of the planetary defense community is to identify at least several decades in advance any object on a collision course with Earth, because several decades of warning is roughly what is needed to implement a kinetic impactor or other deflection strategy while the object is still far enough away that a small velocity change translates into a large positional change by the time it reaches Earth's orbit. The mathematics of orbital mechanics means that deflecting an impactor 10 years out requires far less energy than deflecting it 10 months out, which in turn requires far less energy than is needed even 10 days before impact. Sedna is one of the most intriguing and poorly understood objects in the outer solar system. Discovered in 2003 by Mike Brown, Chad Trujillo, and David Rabinowitz, the same team that discovered Eris, Sedna is a large trans-Neptunian object, probably between 800 and 1,000 kilometers across, orbiting the Sun on an extraordinarily elongated ellipse. Its closest approach to the Sun is about 76 astronomical units, more than twice Neptune's distance, and its farthest point is about 937 astronomical units. Its orbital period is about 11,400 years. What makes Sedna truly strange is that its orbit should not exist. All known trans-Neptunian objects that formed in the outer solar system have closest approaches below about 50 astronomical units, because beyond that distance, the gravitational influence of Neptune is insufficient to place objects onto Sedna-like orbits. Sedna's perihelion is too far for Neptune to have put it there. Some mechanism must have lifted its perihelion outward. Proposed explanations include a close stellar encounter in the Sun's birth cluster. Many stars pass close to each other in dense stellar nurseries before dispersing, that gravitationally perturbed some objects into high perihelion orbits, or the influence of a hypothetical large planet in the outer solar system, the same Planet 9 hypothesis proposed to explain the clustering of other extreme trans-Neptunian objects, or possibly the gravitational influence of passing stars over the Sun's galactic lifetime. Sedna remains a clue without a clearly identified crime. A second Sedna-like object, 2012 VP-113, was discovered in 2012, which makes a stellar encounter explanation more plausible, but does not rule out the planet hypothesis. The outer solar system is almost certainly more populated and more complex than current surveys reveal. The Arrokoth encounter by New Horizons in January 2019, a flyby of a contact binary Kuiper belt object about 6.5 billion kilometers from the Sun, was the most distant exploration of a solar system body in history and produced the most pristine view yet of what the building blocks of the outer solar system look like. Arrokoth, informally nicknamed Ultima Thule before receiving its official name, consists of two lobes that gently merged at very low speed, a process called accretion that left the object's original structure almost entirely intact, unlike the shattered rubble piles that asteroid impacts create. Its color is uniformly red, produced by organic molecules called tholins, created by cosmic radiation acting on the methane and nitrogen ices of the outer solar system, and there is no visible evidence of resurfacing or geological activity. Arakoth is likely a time capsule from the earliest phase of solar system history, a relic of the gentle pebble accretion process that preceded the more violent planetary building. Its shape, two lobes gently touching, is consistent with a model in which two initially separate bodies formed together in the same collapsing gas cloud and very slowly spiraled together through mutual gravitational attraction in the low-velocity environment of the early Kuiper belt. The question of what the early solar system looked like in its first million years, before the planets had grown to their current masses, when the protoplanetary disk was still a complex, turbulent environment of gas and dust and growing planetesimals, is one that planetary scientists approach from multiple angles simultaneously. Meteorites provide a geological record of the early disk, the oldest objects in the solar system, calcium-aluminum-rich inclusions found in carbonaceous chondrite meteorites, formed by condensation from the hot gas near the young sun at about 4.567 billion years ago, with an accuracy of better than 1 million years. Chondrules, tiny spherical droplets of once molten silicate, found in the same meteorites, record flash heating events in the early disk, where some mechanism briefly melted millimeter-scale bodies to temperatures of about 2000 Kelvin within minutes, and then cooled them almost as quickly. What caused chondrule-forming events is one of the long-standing unsolved problems of meteoritics. Proposed mechanisms include shock waves propagating through the disk, lightning in the disk's electrostatic environment, and the bow shocks produced by planetesimals moving through the gas at supersonic speeds. Each chondrule is a frozen record of a specific heating event that occurred 4.5 billion years ago. And every time we slice open a meteorite, we are reading a message from before the planets existed. The concept of an interstellar civilization and the technology it would need to become one has been explored mathematically through what is called the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964 as a way of classifying civilizations by their energy use. A Type 1 civilization controls all the energy available on its home planet, on the order of 10 to the 16th watts. Earth's current civilization uses about 2 times 10 to the 13th watts, making us about a Type 0.7 on Kardashev's scale. A Type 2 civilization harnesses all the energy output of its home star, roughly 10 to the 26th watts for a sun-like star. A Type 3 civilization controls the energy of an entire galaxy, roughly 10 to the 37th watts. The progression represents not just energy, but the kind of engineering required to use it. A Type 2 civilization might build a Dyson sphere, a structure surrounding a star that captures all its radiation, first theorized by Freeman Dyson in 1960, who pointed out that an expanding civilization would eventually want to use all available solar energy, and that the most efficient way to do so would be some form of structure enclosing the star. The heat from such a structure's outer surface would be detectable as an anomalous infrared source, a star-sized object glowing at a temperature too low for its luminosity. Infrared surveys searching for Dyson sphere candidates have been conducted, finding some anomalous objects, but none that cannot be explained by natural phenomena like circumstellar dust shells around evolved stars. The search continues. The physics of wormholes, hypothetical tunnels through spacetime connecting two distant points, are permitted by the mathematics of general relativity, but the conditions required to keep one open are extraordinarily demanding. A traversable wormhole requires what is called exotic matter, material with negative energy density, to prevent the tunnel from collapsing under gravity. Negative energy density is not entirely without physical basis. The Casimir effect, observed in laboratories, demonstrates that the energy of the quantum vacuum between two closely spaced conducting plates is slightly less than the vacuum energy outside them, a small but measurable negative energy density that arises from the quantum mechanics of vacuum fluctuations constrained by the boundary conditions. But the amount of negative energy achievable in any known physical process is so far below what would be needed to stabilize a macroscopic wormhole as to be negligible. Whether a civilization with sufficient technological capability could engineer exotic matter in the quantities needed, and whether the laws of physics ultimately permit it, is an open question that sits at the intersection of general relativity, quantum field theory, and thermodynamics. Some physicists consider traversable wormholes physically possible in principle, but engineering impossible in practice. Others believe that deeper physical principles like the holographic principle, which relates the information content of a region of space to its boundary area, or the ER=PR conjecture, which proposes that quantum entanglement between particles is physically equivalent to a microscopic wormhole connecting them, may impose fundamental restrictions that rule out traversable wormholes of any scale. The holographic principle itself is one of the most conceptually radical ideas in modern theoretical physics. Arising from the work of Gerard 't Hooft and Leonard Susskind in the 1990s, inspired by Stephen Hawking's work on black hole thermodynamics and Jacob Bekenstein's discovery that the entropy of a black hole is proportional to the area of its event horizon rather than its volume, the holographic principle proposes that all the information needed to describe the physics of a three-dimensional region of space is encoded on the two-dimensional boundary of that region, just as the information in a three-dimensional hologram is encoded on a two-dimensional surface. The most concrete realization of this idea is the AD-S/FT correspondence, proposed by Juan Maldacena in 1997, which establishes a mathematical equivalence between a theory of gravity in a certain type of curved spacetime and a quantum field theory living on the boundary of that space, with no gravity at all. This duality has been used as a theoretical tool to study both quantum gravity and strongly coupled quantum field theories, producing insights that would have been inaccessible with either theory alone. It also raises the deeply uncomfortable possibility that the three-dimensional world we experience, with its solid objects and spatial depth, may be, in some mathematical sense, equivalent to a two-dimensional description without gravity. Whether this constitutes a meaningful statement about the nature of reality, or simply a mathematical equivalence without ontological implications, is debated. The fine-tuned universe, the observation that the fundamental constants of physics appear to be extraordinarily precisely set to values that permit the existence of complex structures, chemistry, and life, is one of the most philosophically loaded topics in science. If the strong nuclear force were a few percent weaker, protons and neutrons would not bind together into nuclei, and chemistry would be impossible. If the cosmological constant, the energy of the vacuum, were any larger than its actual value by many orders of magnitude, the universe would have expanded too fast for gravity to form any structures at all. If the ratio of electromagnetic force to gravitational force were significantly different, stars could not maintain the right balance of pressure and gravity to burn steadily for billions of years. These coincidences, and there are many more of them, can be interpreted in several ways. They might indicate that we are missing a deeper theory from which the constants emerge as necessary consequences. They might indicate that there are many universes, each with different constants, and we inevitably find ourselves in one where the constants permit our existence, the anthropic principle. Or they might simply be coincidences, and the appearance of fine-tuning might dissolve once we understand the physics more deeply. None of these explanations is fully satisfying. All of them have serious physicists defending them. The multiverse, the idea that our observable universe is one of an enormous or infinite number of distinct universes, arises naturally from several physical theories. Eternal inflation, the leading theoretical framework for understanding the physics of the early universe, predicts that the inflationary process continues forever in an exponentially growing background spacetime, with new bubble universes, each potentially with different physical constants, different particle content, different laws, nucleating continuously from the inflating background. Our universe would be one such bubble, its constants determined by the specific vacuum state it settled into after inflation ended. In eternal inflation, the number of other bubble universes is likely infinite, and the distribution of their properties is governed by whatever determines the landscape of possible vacuum states in the underlying physics. A landscape that, in string theory, contains an estimated 10 to the 500 distinct vacuum states. Each would produce a universe with different physical characteristics. Most would be sterile. We, inevitably, are in one that is not. The question of what came before the Big Bang, approached differently by loop quantum cosmology, suggests that the Big Bang was not a true beginning but a bounce, a moment when a previously contracting universe reached its maximum density and rebounded into expansion. In loop quantum cosmology, quantum gravitational effects that become important at the Planck scale, densities of about 5 times 10 to the 96th kilograms per cubic meter, prevent the singularity that general relativity predicts and replace it with a bounce. The equations can be evolved backward through the bounce to describe the contracting phase that preceded it. The contracting pre-bounce universe would have had its own structure, its own large-scale distribution of matter, its own imprint that might in principle be detectable in the statistical properties of the CMB or the large-scale structure of our universe. Whether this is testable in practice depends on how much information survives the bounce. Some calculations suggest that quantum effects at the bounce would scramble most of the pre-bounce information, making it effectively unobservable. Others suggest that certain statistical signatures might survive. The question has moved from pure philosophy into physics that is at least conceivably testable. The future of the sun is a story that begins not with drama, but with gradual, almost imperceptible change. The sun has been burning for about 4.5 billion years, and has roughly 5 billion more years on the main sequence before its hydrogen fuel is exhausted. During that time, it will continue to brighten slowly, luminosity increasing by about 10% per billion years. In about 1 to 2 billion years, the sun will be bright enough to push Earth's average surface temperature above the boiling point of water, triggering a runaway greenhouse effect that will turn Earth into something more like Venus. Long before that, perhaps in 500 million to a billion years, the increasing solar luminosity will disrupt the carbonate-silicate cycle that regulates Earth's carbon dioxide levels, reducing atmospheric CO2 to concentrations too low for most plant photosynthesis, ending the biosphere as we know it, even if liquid water remains. The window of habitability on Earth, in the long view, is already past its midpoint. We arrived late in the habitable era. When the sun finally exhausts its core hydrogen in about 5 billion years, it will expand into a red giant, engulfing the inner planets and possibly Earth. But before that process, there is a subtler event. As the helium ash accumulates in the core and hydrogen burning continues in a shell around it, the sun will expand and cool on the outside while the core contracts and heats. When the core reaches about 100 million Kelvin, helium fusion will ignite in an explosive event called the helium flash, a thermonuclear runaway in the degenerate core that releases an enormous amount of energy in a matter of minutes, but one contained entirely within the star's deep interior, not detectable from outside. The helium flash restructures the solar interior and sets the sun on the horizontal branch of the Hertzsprung-Russell diagram, burning helium steadily for about 100 million years. Then helium is exhausted, and the final ascent up the asymptotic giant branch begins. The sun's outer layers will be expelled in multiple pulses driven by thermal pulsations of the helium-burning shell, creating a planetary nebula of glowing gas surrounding the exposed core, which will cool and fade for billions of years as a white dwarf. The sun's planetary nebula, if anyone were watching from a distant star 4 to 5 billion years from now, would be briefly one of the most beautiful objects in the galaxy. No one is here yet to watch it happen on our end. Space archaeology, the use of satellite imagery to identify, map, and monitor archaeological sites from orbit, has become one of the most transformative tools in the history of archaeology over the past few decades. Satellites equipped with multispectral cameras can detect subtle variations in soil composition, moisture, and vegetation that betray the presence of buried walls, foundations, roads, and other structures invisible from the ground. Sites in the Amazon, once dismissed as incapable of supporting large pre-Columbian civilizations because of the poor soil, have been found to contain vast networks of earthworks, causeways, and geometric enclosures visible in high-resolution satellite and LiDAR data, evidence of complex societies that transformed the landscape for thousands of years before European contact. In the Middle East, Corona reconnaissance satellite imagery from the 1960s, declassified decades later, has been used to identify thousands of ancient sites that have since been destroyed by development, agriculture, or conflict, creating a historical record of a landscape that no longer exists. The same satellite imagery has documented the large-scale looting of archaeological sites in Syria and Iraq during and after the conflicts of the 2010s, with crater patterns from illicit digging spreading across satellite time series like a spreading stain. The sky, which we use to look outward at the universe, also looks back at us, documenting what we have built and what we are destroying. The Outer Space Treaty of 1967 is the foundational document of international space law, signed by the United States, the Soviet Union, the United Kingdom, and subsequently most spacefaring nations. It establishes that outer space, including the moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by use, or by any other means. It prohibits the placement of nuclear weapons or other weapons of mass destruction in space or on celestial bodies. It reserves the moon and other celestial bodies for peaceful purposes, and it establishes that astronauts are envoys of all humanity to be assisted by any nation in distress. What it does not clearly resolve is whether private entities can own resources extracted from celestial bodies, even if they cannot claim sovereignty over the bodies themselves. The United States addressed this ambiguity in 2015 with the Commercial Space Launch Competitiveness Act, which explicitly authorized American citizens and companies to own and sell resources extracted from asteroids and other celestial bodies. Luxembourg and the United Arab Emirates have passed similar legislation. Other nations have not, and the legality of asteroid mining under existing international law remains a genuine and unresolved question that will become practically important as asteroid mining technology matures. The military dimension of space, always present beneath the surface of civilian programs, has become more explicit in recent decades. China and Russia have developed and tested anti-satellite weapons capable of destroying objects in low Earth orbit, producing in the process significant debris fields that threatened other satellites and the International Space Station. The United States established the United States Space Force in December 2019, the first new branch of the American military in over 70 years, explicitly organized around the protection of American space assets and the development of space-based military capabilities. The militarization of space, the use of satellites for intelligence, navigation, communication, and targeting, has been ongoing since the earliest days of the space age, but the weaponization of space, the placement of offensive capabilities in orbit, raises legal and strategic questions that the existing treaty framework is not well equipped to handle. The ability to blind or destroy an adversary's navigation and communications satellites in the opening hours of a conflict is now a recognized strategic capability, which creates incentives for the rapid development and deployment of protective and offensive space capabilities that existing arms control agreements do not address. The question of what it means to look up at the night sky and see patterns, to organize the random distribution of stars into constellations, to find meaning and narrative in what is, at one level of description, simply the projection of stars at enormously varying distances onto a sphere, speaks to something fundamental about how human minds process the world. The constellations are not real configurations of stars in space. Orion, for instance, is a projection of stars at distances ranging from a few hundred to a few thousand light-years onto a two-dimensional surface. The stars that make up the Hunter's Belt, Alnitak, Alnilam, and Mintaka, are roughly 800 to 1,000 light-years away. Betelgeuse, the red giant at Orion's shoulder, is about 700 light-years. Rigel, the blue supergiant at his foot, is about 860. None of these stars are neighbors. They are scattered through a large volume of space and happen to fall along similar lines of sight from Earth's vantage point. In a few million years, as the Sun moves through the galaxy and the stars move through their own orbits, these alignments will dissolve and new ones will form, and every constellation we know will be unrecognizable. And yet the patterns mean something, even knowing this. They have organized human navigation, agriculture, mythology, religion, and poetry for as long as human beings have been capable of organizing anything. The same stars that are physically meaningless groupings of distant suns are deeply meaningful groupings of human history. Every culture's contact with the sky, every sailor who found north by Polaris, every farmer who planted by the rising of the Pleiades, every child who was told a story about the hunter, or the bear, or the scorpion. The sky is simultaneously a physical reality of almost incomprehensible scale and complexity, and a cultural object of almost infinite human significance. Both things are true at once. The universe does not choose between them, neither should we. There is a concept in astrophysics called the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. Because the universe is 13.8 billion years old and light travels at a finite speed, the farthest we can see corresponds to the distance light could travel in 13.8 billion years. But because the universe has been expanding during that time, the actual distance to the edge of the observable universe is not 13.8 billion light-years, but about 46 billion light-years, the co-moving distance accounting for the expansion of space. Everything within that sphere is in principle observable to us. Everything beyond it is not because it does not exist, but because light from it has not had time to reach us. As the universe ages, more light arrives from greater distances, and the observable universe grows. A dark energy is accelerating the expansion, and at some point in the far future, the rate of expansion beyond a certain distance will exceed the speed of light, and the cosmological horizon will actually begin to shrink. Events beyond the horizon will be forever cut off from our future. Information that is currently available to future observers will eventually be lost. The universe, in its old age, will become less knowable, not more. This asymmetry in time, that the universe grows less knowable, not more, as it ages, is one of the most profound and melancholy facts in cosmology. We live in a privileged epoch, early enough that the CMB is still detectable, that galaxies are still visible in all directions, that the universe's structure is still legible. Future civilizations in the far future of a dark and expanding universe will look out at an empty sky and know less than we do. They will have fewer data, not more. The evidence for the Big Bang, the evidence for other galaxies, the evidence for the structure of the cosmos, all of it will eventually be out of reach, redshifted and dimmed and carried over the cosmological horizon. We are, in a very specific and physical sense, lucky to be here now. The work of science is to take advantage of that luck, to measure while the universe is still visible, to record while the record can still be made, to ask questions while answers are still, in principle, available. The astronomers, physicists, and engineers who build the instruments and send the missions and analyze the data are not doing something separate from ordinary human life. They are doing the most human thing possible, refusing to accept ignorance when knowledge is within reach. Every discovery changes what is possible next. Every answered question opens 10 more. The universe is not running out of questions. It is, if anything, producing them faster than we can ask them. The sky above your head right now contains light from the oldest objects we can see and the youngest we can measure. It contains the light of stars that will never be visited and signals from objects that no human eye will ever observe directly. It contains the gravitational echoes of collisions that happened when the universe was a fraction of its current age. It contains the future of every element that will ever be synthesized and scattered into new generations of worlds. It contains more than we know how to look for, more than we know how to name. We have been pointing our instruments at it for a few centuries with any real precision and for a few decades with the sensitivity needed to hear its whispers. We have barely started, and it is still showing us things we have never imagined. That is not likely to change anytime soon. The universe has been doing this for 13.8 billion years. It shows every sign of continuing. The Pioneer anomaly is a chapter in the history of science that illustrates how carefully a mystery must be examined before you reach for a revolutionary explanation. Pioneer 10 and Pioneer 11, spacecraft launched in 1972 and 1973 to explore the outer solar system and become the first human-made objects intentionally sent toward interstellar space, were tracked with extraordinary precision for decades after their launch using the Doppler shift of their radio signals. By the late 1990s, analysts noticed that both spacecraft were decelerating very slightly more than the known forces of solar gravity, solar radiation pressure, and planetary gravitational influences could account for. The anomalous deceleration was tiny, roughly 8 times 10 to the negative 10 meters per second squared, but consistent across both spacecraft and persistent over years of tracking. It became known as the Pioneer anomaly, and it attracted enormous attention as a possible sign of new physics, a deviation from known gravity laws at large distances, perhaps a hint of dark matter effects, perhaps a sign of some undiscovered force. Some theorists proposed modifications to Newtonian dynamics that would naturally produce such an effect. The resolution, which came after years of careful analysis published in 2012, was mundane but required extraordinary effort to prove. Heat radiated asymmetrically from the spacecraft itself, from the radioactive decay of the plutonium in its power source, and from waste heat emitted by the spacecraft electronics, was producing a tiny but persistent thrust in the direction opposite to the Sun, mimicking the signature of an anomalous deceleration. The effect had been overlooked in earlier analyses because it required a detailed thermal model of the spacecraft geometry, material properties, and power output over the entire mission. When that model was built using recovered archival data from the original mission, it accounted for the anomalous deceleration completely. There was no new physics. There was spacecraft engineering, very carefully ignored, producing a subtle and persistent effect that looked for a time like something profound. The Pioneer anomaly is now taught as an important case study in the difficulty of precision measurement and the danger of premature theoretical excitement. The Cassini division, the most prominent gap in Saturn's ring system, about 4,800 kilometers wide, visible through even a modest telescope, and giving the rings their iconic separated appearance, is not actually empty. It contains diffuse, thin ring material and occasional moonlets and clumps. What makes the Cassini division a gap in the sense of dramatically reduced density is a resonance with Saturn's moon Mimas. Any ring particle in the Cassini division would have an orbital period exactly half of Mimas's orbital period, so it would receive a gravitational kick from Mimas at the same point in every orbit, accumulating a perturbation that eventually destabilizes the orbit and pushes the particle out of that region. This is a Kirkwood gap, the same mechanism that produces gaps in the asteroid belt at resonances with Jupiter. The shepherd moons of Saturn, small moons that orbit at the edges of ring gaps and features, their gravity sculpting the ring boundaries through similar resonance effects, were predicted before they were found, based on the observed sharpness of certain ring edges that could not be maintained without a confining force. The Voyager missions found the shepherd moons right where orbital mechanics said they had to be. Saturn's north polar hexagon is one of the most geometrically striking and scientifically puzzling features in the solar system. A persistent hexagonal cloud pattern at Saturn's north pole, about 30,000 kilometers across, larger than Earth, has been continuously observed since the Voyager flybys in 1980 and 1981 through the entire Cassini mission, and in ground-based observations. The hexagon persists for decades, maintaining its sharp corners and straight sides while everything else in Saturn's atmosphere swirls and changes. Laboratory experiments with rotating fluid tanks have reproduced hexagonal jet stream patterns, and the Saturnian hexagon is believed to be a standing wave pattern in the polar jet stream, locked in place by the geometry of the atmospheric dynamics and the interaction between the jet stream and wave perturbations. But the precise conditions that maintain it at Saturn and produce 6 sides rather than 5 or 7, and that have kept it stable for at least 40 years of observation, are not fully reproduced by current atmospheric models. The hexagon changes color with Saturn's seasons. It was a brownish gold when Voyager saw it in winter, turned blue during the years Cassini observed it in late winter and spring, and has been tracked shifting back toward gold as summer approaches. The color change is attributed to changes in the photochemical production of hazes in the atmosphere as the amount of sunlight reaching the polar region varies through Saturn's 29-year year. RR Lyrae stars are a class of variable star that serve as one of the most important distance indicators for old stellar populations in the galaxy. Like Cepheid variables, RR Lyrae stars pulsate in a regular and predictable way, and their pulsation period is related to their intrinsic luminosity, though for a much narrower range of luminosities than Cepheids, which makes them effective standard candles for a different population of stars. RR Lyrae stars are old, metal-poor stars found primarily in globular clusters and the galactic halo, the same population of ancient stars that formed early in the Milky Way's history. Their pulsation periods range from about a quarter of a day to about 1 day, making them easy to identify in time series photometric surveys. By measuring the apparent brightness and pulsation period of RR Lyrae stars in a globular cluster, astronomers can determine the cluster's distance with good accuracy. And because RR Lyrae stars are old enough to be present in essentially any ancient stellar system, they can be used to measure distances to the galactic halo, to nearby dwarf galaxies, and to the nearest spiral galaxies. Mira variables, pulsating red giant stars with periods of months to years, are a third class of pulsating standard candle, important for tracing the distance scale in the nearby universe and particularly useful for measuring the distances to other spiral galaxies in the local group. The Sloan Great Wall, identified in the Sloan Digital Sky Survey data in 2003, is a filamentary structure of galaxies spanning about 1.4 billion light-years, making it, at the time of its discovery, the largest known structure in the universe. It subsequently lost that title to larger structures including the Hercules Corona Borealis Great Wall, discovered in 2013. The Sloan Digital Sky Survey itself, which mapped the distribution of millions of galaxies across a large portion of the sky in unprecedented detail, produced the first precise maps of baryon acoustic oscillations in the galaxy distribution, the same feature that cosmologists use as a standard ruler to measure the expansion rate of the universe. The SDSS also identified thousands of quasars, hundreds of thousands of spectroscopically confirmed galaxy clusters, and mapped the three-dimensional large-scale structure of the universe in a volume that transformed our picture of the cosmic web from a sketch into a detailed atlas. The Buddha's void is one of the most unsettling features of the observable universe on intermediate scales. It is a roughly spherical region of space about 330 million light-years across, located about 700 million light-years from Earth in the direction of the constellation Buddhas, that contains far fewer galaxies than expected. Not empty, it contains about 60 known galaxies, but dramatically underdense compared to the surrounding cosmic web. If the Buddha's void were typical of cosmic structure, the universe would look very different from what we observe. It is an enormous bubble in the cosmic web, a void on a scale that challenges simple models of structure formation. Voids are a normal feature of the large-scale structure. The cosmic web consists of filaments of matter surrounding sheets and clusters, with vast empty regions in between. But the Buddha's void is larger than most models predicted as common and was for many years the largest known void. The existence of such voids raises questions about the uniformity of the universe on the scales where cosmologists expect it to be approximately homogeneous, scales above a few 100 million light-years. The Buddha's void is either an outlier in the statistical distribution of void sizes, or a hint that the universe is clumpier on very large scales than the standard model predicts. The CMB cold spot is a related anomaly at the largest scales. In the map of the cosmic microwave background, there is a region about 5 degrees across, 10 times the size of the full moon in the sky, centered in the southern hemisphere of the CMB map, in the constellation Eridanus, that is significantly colder than its surroundings. This is not a temperature difference in absolute terms. The CMB is already only 2.7 Kelvin, and the cold spot is only about 70 microkelvins colder than average. But that difference, given the otherwise extreme smoothness of the CMB, is statistically surprising. Several explanations have been proposed. One is that the cold spot is caused by a supervoid, an enormous underdense region between Earth and the CMB, producing a slight cooling of CMB photons passing through it via the integrated Sachs-Wolf effect. A supervoid in that direction has indeed been identified at a distance of about 3 billion light-years. But whether it is large enough and deep enough to account for the full cold spot temperature is debated. Another explanation, which has attracted significant theoretical interest, is that the cold spot represents the imprint of a collision between our bubble universe and another bubble universe in the eternal inflation scenario, a literal bruise on the sky from a cosmic collision that occurred during or shortly after inflation. If this explanation were correct, it would be the first observational evidence of another universe. The evidence is suggestive but not conclusive, and the question is genuinely open. The Arecibo message, transmitted toward the globular cluster M13 on November 16, 1974, was the first deliberate attempt by humanity to send a targeted radio message toward another possible civilization. The message was transmitted by the Arecibo radio telescope, at the time the largest single-dish radio telescope in the world, with a 300-meter reflector built into a natural bowl in the karst landscape of Puerto Rico, at a frequency of 2400 MHz, at a power of approximately 1 megawatt. The message encoded in binary a pictorial representation of basic mathematical and scientific information, the numbers 1 through 10 in binary, the atomic numbers of the elements hydrogen, carbon, nitrogen, oxygen, and phosphorus, the elements of DNA, the formulas for the sugars and bases of the DNA double helix, an image of the double helix itself, a figure of a human being with their height indicated, a schematic of the solar system with Earth highlighted, and a schematic of the telescope itself. It was 23 characters wide and 73 characters tall, dimensions chosen because 23 and 73 are prime numbers, a mathematical hint that the array of binary digits is meant to be assembled into a two-dimensional image. M13 is about 25,000 light-years away. The message will arrive in roughly 25,000 years. Any reply, traveling at the speed of light, would take another 25,000 years to return, 50,000 years round trip. This is not a communication. It was a demonstration, a technological proof of concept, and a cultural statement, not a practical attempt at conversation across interstellar distances. The choice of M13, a globular cluster, was itself questionable from a SETI perspective. The stars in globular clusters are ancient and metal-poor, which means the rocky planets needed for life as we know it are rare, and the environment inside a dense globular cluster is dynamically unstable for planetary systems on long timescales. But the symbolic gesture mattered, and the Arecibo message remains one of the most famous single transmissions in human history. The Voyager Golden Record, attached to both Voyager 1 and Voyager 2, is a more elaborate attempt at interstellar communication, though one without a specific destination, since both Voyagers are heading in the general direction of interstellar space with no particular star as a target. The records, 12-inch gold-plated copper discs, contain sounds and images of Earth, music from Bach, Beethoven, Chuck Berry, traditional music from dozens of cultures, greetings in 55 human languages, natural sounds including rain, surf, thunder, singing birds, whales, and human laughter, and a series of 116 images encoded as analog signals, showing the sun, the planets, human anatomy, landscapes, food, cities, and scientific instruments. The records include instructions for playback encoded in the cover of the disk itself, referencing the spin transition frequency of hydrogen, the most fundamental electromagnetic frequency in the universe, as a unit of time, and the position of the Sun relative to 14 known pulsars as a galactic address. Carl Sagan, who led the committee that assembled the record's contents, described it as a message in a bottle thrown into the cosmic ocean. The probability that any intelligence will ever find and decode it is extraordinarily small. The probability that it exists, that we made it, that it is out there right now traveling through the interstellar medium at 17 kilometers per second, that is 100%. The radio telescope at Arecibo collapsed on December 1, 2020, when two support cables failed in rapid succession, causing the instrument platform suspended above the reflector dish to fall. The collapse destroyed the dish and ended 57 years of operation at one of the most scientifically productive astronomical instruments ever built. Arecibo had been used to study pulsars, radar map the surfaces of Venus and near-Earth asteroids, discover the first binary pulsar system for which the Nobel Prize in Physics was awarded in 1993, detect the first exoplanets around a pulsar, not a main sequence star, announced in 1992, and conduct the world's largest SETI observations. Its loss was mourned by the scientific community as the loss of a unique capability, particularly in planetary radar, the ability to bounce radio signals off near-Earth asteroids and precisely map their surfaces and refine their orbits. No equivalent planetary radar facility currently exists, and the scientific loss is real and ongoing. The search for life has increasingly focused not just on detecting biosignatures in exoplanet atmospheres, but on understanding the origin of life in enough detail to know how likely it is to arise under the right conditions. The transition from chemistry to biology, abiogenesis, requires several things to happen: the formation of monomers like amino acids and nucleotides, their polymerization into longer chains, the emergence of self-replication, and the formation of compartments, membranes, or other boundaries that allow the concentrations of reactive molecules to build up and selection to operate. None of these steps is well understood at the mechanistic level, and the step that is least understood is how RNA or some predecessor molecule first achieved self-replication, how the first molecule arose that could template the synthesis of a copy of itself. The RNA world hypothesis proposes that the first self-replicating molecules were RNA molecules, and that RNA both carried genetic information and catalyzed chemical reactions, functions now divided between DNA and proteins in modern cells. RNA can do both, as shown by the discovery of ribozymes, RNA molecules that catalyze chemical reactions including, crucially, the joining of RNA nucleotides. The ribosome, the universal machinery of protein synthesis present in every living cell on Earth, is essentially an RNA machine. Its catalytic core is RNA, and the protein components are structural accessories. This is a strong argument that RNA was central to the origin of life, but demonstrating how sufficiently long and functional RNA molecules could arise spontaneously from simple chemistry under plausible prebiotic conditions remains an active research challenge. The first RNA self-replicators, if they existed, would have been imperfect and error-prone, and the transition from chemical self-replication to biological heredity, with its enzymatic error correction and elaborate genetic code, would have required an enormous series of steps whose probability is genuinely unknown. What we do know is that life on Earth has been extraordinarily persistent once it began, and extraordinarily creative in exploiting any available energy source. The discovery of life around hydrothermal vents in the deep ocean in 1977 by the submersible Alvin off the Galapagos was one of the most unexpected biological discoveries of the 20th century. Dense communities of organisms, tube worms up to 2 meters long, giant clams, white crabs, fish, living in total darkness at pressures of 200 atmospheres, supported not by photosynthesis but by chemosynthesis, the oxidation of hydrogen sulfide and other chemicals released by the vents. The primary producers in these ecosystems are bacteria and archaea that use the chemical energy of the vent fluid rather than sunlight. Everything else in the food chain depends on them, and the sun might as well not exist from the perspective of the vent community. This discovery fundamentally changed the boundaries of the biosphere, the portion of Earth in which life exists, and by extension changed what environments elsewhere in the solar system might be considered habitable. Anywhere there is chemical energy and liquid water, life might find a way. Anywhere chemical energy and liquid water coexist, we should look. The Fermi paradox, revisited with all of this context, has a particular edge that the simple statement of it often lacks. We have now confirmed that planets are extraordinarily common, that organic molecules form spontaneously throughout the galaxy, that liquid water likely exists beneath the ice of multiple moons in our own solar system, and that the galaxy is old enough that a civilization arising 1 billion years before us, which is a plausible timescale given that terrestrial planets have been forming throughout the galaxy's history, would have had ample time to colonize every star system in the Milky Way at speeds far below the speed of light. 1 billion years is 220 galactic orbits, at 1/10 the speed of light, achievable with nuclear pulse propulsion technology that was theoretically worked out in the 1950s. A civilization could cross the Milky Way in about 1 million years, at 1% of the speed of light in 100 million years. Even accounting for the time needed to establish each new colony before it begins launching its own missions, the galaxy should be full, and it appears, to every measurement we have made, not to be. Whatever explains this absence, the rarity of life, the rarity of intelligence, the self-destruction of civilizations, deliberate concealment, our failure to recognize the signatures of non-human technology, the explanation matters enormously. It may be the most important fact about the universe that we do not yet know. The night sky, then, is simultaneously a record of what the universe has been, a window into what it is, and a question about what else is in it. Every photon that reaches your eye from a distant star has traveled across millions of years, through the interstellar medium, through the solar wind, through the atmosphere of this planet to reach the thin film of photoreceptors at the back of your eye that converts it to an electrochemical signal that your brain interprets as light. That chain of events, from nuclear fusion in a stellar core to conscious perception on a rocky planet, spans distances and timescales that dwarf anything in ordinary human experience. And it happens billions of times every second, in every pair of eyes that has ever looked at the sky. The universe has been sending its light to this planet for as long as the planet has existed. We have been intercepting it consciously for a tiny fraction of that time. We are just beginning to understand what it is trying to tell us. The scale of what we do not know is not a reason for despair. It is the whole point. Science is not a project of cataloging what is already known. It is a project of pushing at the boundary between the known and the unknown, finding it further out than expected every time, and pushing again. The universe rewards that persistence. It has been doing so for as long as we have been asking. Every answered question opens a view of something larger and stranger and more worth wondering about. The universe does not have a bottom. It does not have an end to its strangeness. It goes all the way down and all the way out, and as far back as physics can reach, and further than we have yet looked. That is not a limitation. That is an invitation. The James Webb Space Telescope's observations of the earliest galaxies have produced one of the most striking disconnects between theory and observation in recent astronomical history. Models of galaxy formation built over decades and calibrated against older observations predicted that the universe in its first 500 million years would be populated primarily by small, irregular, slowly assembling protogalaxies, with the large, structured spiral and elliptical galaxies we know today arriving much later after billions of years of merging and growth. What Webb actually found was a population of surprisingly massive, surprisingly bright, and in some cases surprisingly well-organized galaxies at redshifts corresponding to the universe being only 3 to 5% of its current age. Some of these early galaxies contain stellar masses that seem to require star formation rates far in excess of what the Standard Model predicts for those conditions, forming stars so fast that some theorists have described the problem as galaxies that seem to have formed too many stars too quickly in a universe that should not have had enough time or enough dense gas to permit it. The theoretical response to these observations has been active and varied. Some researchers have proposed modifications to the initial mass function of stars in the early universe. Perhaps the first galaxies formed more of their mass in massive, highly luminous stars than galaxies do today, making them brighter per unit mass. Others have proposed that the efficiency of converting gas into stars was simply higher in the early universe, when gas densities were greater and the competing effects of stellar feedback were less well established. Others have proposed modifications to the properties of dark matter. Perhaps dark matter behaved differently in the early universe, Or perhaps some fraction of dark matter decays or interacts in ways that altered the early structure formation. And some have proposed more radical ideas, including modifications to inflation itself, or departures from the standard cosmological model at the level of the growth of structure in the early universe. The observations are real and well established. The interpretation is very much in flux. This is science working exactly as it should, a new instrument revealing something unexpected, the field scrambling to understand it, and the result being a sharper and more accurate understanding of how the universe actually works, rather than how our models assumed it did. The Parker Solar Probe's close passes of the Sun have also overturned some long-held assumptions about the solar wind structure very close to the source. One of the most striking discoveries has been the prevalence of switchbacks, rapid reversals of the magnetic field direction in the solar wind, where the field briefly flips by 180 degrees before returning to its original orientation. These structures were known from earlier spacecraft, but their abundance and their locations so close to the Sun were unexpected. The switchbacks produce local increases in solar wind speed and carry enhanced fluxes of energetic particles. They appear to be launched from the Sun's surface, possibly connected to the dynamic activity of supergranulation cells, large convective cells in the photosphere that organize the solar magnetic field into a network of concentrated field lines at their boundaries, but the detailed mechanism is still being worked out. What the switchbacks definitively demonstrate is that the solar wind is not a smooth, steady outflow, but a structured, turbulent medium even before it has traveled far from its source, and that the transfer of energy from the solar surface to the corona and solar wind involves localized, impulsive events rather than or in addition to wave heating operating uniformly across the corona. Ion propulsion, the technology that drives spacecraft through the controlled acceleration of charged particles rather than chemical combustion, has transitioned in the past few decades from an exotic laboratory concept to a mature operational technology used on multiple missions. An ion thruster ionizes a propellant, typically xenon gas, and accelerates the ions through an electric field, expelling them from the spacecraft at speeds of 20 to 80 kilometers per second, compared to the 2 to 4 kilometers per second exhaust velocity of chemical rockets. The thrust produced is tiny, comparable to the weight of a sheet of paper on Earth, but it is continuous, and over months and years of operation it accumulates a velocity change that far exceeds what a chemical thruster could achieve with the same mass of propellant. The Deep Space One mission in 1998 was the first deep space mission to use ion propulsion as its primary drive, demonstrating the technology's viability for interplanetary travel. The Dawn spacecraft, which orbited both Vesta and Ceres in the asteroid belt between 2011 and 2018, relied entirely on ion propulsion to achieve the orbital insertions and transfers between two entirely different bodies, something impossible with chemical propulsion given the fuel mass that would require. Japan's Hayabusa and Hayabusa 2 both used ion drives. The Bepi-Colombo mission to Mercury, currently en route, uses solar electric propulsion. Ion drives are now the standard for deep space missions requiring large velocity changes with constrained fuel mass budgets. Nuclear propulsion offers a potential leap beyond chemical and ion propulsion for crewed missions to deep space. A nuclear thermal rocket, in which a nuclear reactor heats propellant to very high temperatures before expelling it through a nozzle, achieves specific impulses roughly twice that of chemical rockets, dramatically reducing the propellant mass needed for a given mission. NASA and the Soviet Union both developed nuclear thermal rockets in the 1960s and 1970s. The American NERVA program produced tested engine designs that were never flown in space, canceled in 1972 along with the rest of the post-Apollo ambition for deep space human exploration. The Soviet Union's equivalent program, RD-0410, also produced tested designs without flight hardware. Interest in nuclear thermal propulsion has revived in recent years, driven by the recognition that crewed Mars missions using chemical propulsion require either very large amounts of propellant, driving up launch mass and mission cost, or very long transit times that expose astronauts to extended cosmic radiation doses. Nuclear thermal propulsion could reduce transit time to Mars from 7 months to perhaps 4 months, staying within accepted career radiation limits and reducing mission complexity. NASA has funded development work on nuclear thermal propulsion with the goal of having flight-ready systems in the 2030s. Nuclear pulse propulsion, the concept explored in the late 1950s and early 1960s under Project Orion, led by Ted Taylor and Freeman Dyson, is far more radical and far more powerful. The idea is conceptually simple. explode nuclear bombs behind the spacecraft, and ride the pressure wave. A pusher plate at the rear of the spacecraft, mounted on a system of shock absorbers, converts the impulse from each explosion into a smooth, continuous acceleration. The specific impulse achievable with nuclear pulse propulsion is far beyond any rocket technology. Some designs proposed by the Orion team would have achieved exhaust velocities of hundreds or thousands of kilometers per second, enabling interplanetary missions measured in weeks rather than months. Dyson, in his original analysis, calculated that a large Orion spacecraft could potentially reach a significant fraction of the speed of light using a magazine of advanced nuclear devices. The project was cancelled in 1963, partly by the Partial Test Ban Treaty that prohibited nuclear explosions in space, partly by the political environment around nuclear weapons, and partly by the ascendance of chemical rockets in the American space program after Kennedy's moon commitment gave NASA a clear near-term focus. Dyson has said that the cancellation of Orion represented a genuine fork in the road of human civilization, that the path not taken might have led to human colonies throughout the solar system by the end of the 20th century. It is the most powerful propulsion concept ever seriously studied, powered by the most destructive weapons human civilization has produced. The Lagrange points, 5 specific locations in any two-body gravitational system where a small object can maintain a stable or semi-stable position relative to the two larger bodies, are some of the most useful real estate in the solar system for spacecraft operations. In the Earth-Sun system, the first Lagrange point, L1, lies between Earth and the Sun at about 1.5 million kilometers from Earth, where the gravitational pull of the Sun and Earth exactly balance, allowing a spacecraft to orbit the Sun at the same rate as Earth without falling toward either. L1 is the location of the Deep Space Climate Observatory, which monitors solar wind approaching Earth, and the original SOHO Solar Observatory. L2, on the opposite side of Earth from the Sun at the same distance, is the location of the James Webb Space Telescope and several other observatories, where a spacecraft can maintain a stable position with the Sun, Earth, and Moon all in approximately the same direction, behind the sun shield of a telescope that needs to keep its detectors extremely cold and its optics shielded from all sources of heat and light. L4 and L5, 60 degrees ahead and behind Earth in its orbit, are the stable Lagrange points where material naturally accumulates. The Trojan asteroids of Jupiter occupy the Jupiter-Sun L4 and L5 points in enormous numbers, with thousands of asteroids sharing Jupiter's orbit at these stable equilibria. Earth has its own Trojan asteroid, 2010 TK7, confirmed in 2011. Though it is small and its orbit is complex, the Lagrange points have been proposed as locations for future space stations, space telescopes, and staging areas for missions deeper into the solar system. The concept of terraforming, reshaping another planet's environment to make it hospitable for Earth life, has moved from science fiction into a subject of serious scientific and ethical analysis over the past few decades. The most discussed candidate is Mars. Mars has carbon dioxide in its atmosphere, water ice at its poles and in the regolith, and a solid surface. The challenge is the thinness of the atmosphere, about 1% of Earth's sea level pressure, the cold temperatures, the lack of a magnetosphere, and the high cosmic radiation environment at the surface. Various proposals for terraforming Mars involve thickening the atmosphere by releasing frozen carbon dioxide from the polar caps, perhaps through manufacturing potent greenhouse gases on the surface, warming the planet enough for liquid water to return to parts of the surface, and eventually introducing photosynthetic organisms to produce oxygen. The timescales involved are enormous, thousands to tens of thousands of years for even optimistic scenarios. Whether the resources of carbon dioxide and water available on Mars are sufficient for terraforming is itself debated. Some analyses suggest Mars may simply not have enough material to produce an Earth-like atmospheric pressure, even if all its frozen reserves were released. The ethical dimension of terraforming is equally complex. If Mars harbors any life, even dormant microbial life in subsurface refugia, terraforming would likely destroy it, introducing Earth organisms that would outcompete any Martian life and fundamentally alter the environment that Martian life, however simple, had occupied for billions of years. The question of whether the potential interests of Martian microbes, if they exist, should constrain human use of Mars is one that philosophers of astrobiology have engaged with seriously. Most working planetary scientists hold the position that we should determine whether Mars is inhabited before making any irreversible decisions about its use, both for scientific and ethical reasons. Carl Sagan, who was in general deeply enthusiastic about the possibility of terraforming Mars, expressed the view that if Mars is dead, it is ours to do with as we choose, but that if it is alive, even in the simplest sense, that changes everything. Planetary protection, the set of policies and practices designed to prevent contamination of other worlds by Earth organisms, and contamination of Earth by extraterrestrial materials, is one of the most practically important applications of astrobiology. The Outer Space Treaty requires nations to conduct their space exploration in ways that avoid harmful contamination of other bodies. NASA and ESA implement this through a system of planetary protection categories. A mission to the Moon requires minimal protection, since the Moon is not considered a candidate for harboring life. A mission to Mars orbiter requires more stringent measures. A mission landing on Mars in a potentially habitable region requires the most stringent Category 4B protocols, in which biological cleanliness of hardware must be verified through bioassay counting of viable organisms and heat sterilization or other decontamination methods. The Perseverance rover, which is searching for signs of ancient life in Jezero crater, was built to the most stringent planetary protection standards NASA has ever applied to a Mars lander, with extensive bioassay testing and specific restrictions on which parts of Mars it is allowed to enter to avoid contaminating regions of potential extant habitability. This is not bureaucratic caution. It is recognition that contaminating another world with Earth organisms, and then finding those organisms and mistaking them for indigenous life, would be one of the most scientifically catastrophic mistakes possible. Every chapter of the space age, from the first satellite to the current era of commercial rockets and interplanetary rovers, has involved people making decisions under uncertainty, sometimes brilliantly and sometimes catastrophically, driven by a combination of scientific ambition, political competition, commercial opportunity, and the simple human compulsion to see what is over the next horizon. That compulsion has produced, in the span of a single human lifetime, the transformation of our species from one that knew almost nothing about the other planets, to one that has placed instruments on every planet, on comets, on asteroids, and on moons across the outer solar system. It has produced photographs of the surfaces of Mars and Titan and Pluto. It has detected gravitational waves from black holes a billion light-years away. It has found thousands of worlds around other stars. It has mapped the cosmic microwave background to 1 part in 100,000. It has measured the age of the universe to within 1%. All of this in less than a century of concerted effort. What the next century produces, what instruments are built, what missions are launched, what questions are answered, and what new ones replace them, depends on choices that are being made now and will be made in the coming decades. The choice to fund large observatories or not. The choice to send humans beyond low Earth orbit or not. The choice to invest in planetary defense. The choice to look seriously for life on Europa and Enceladus. The choice to develop new propulsion systems that make the outer solar system accessible on human timescales. These are not purely scientific choices. They are political and economic and social choices, made by societies that may or may not prioritize the long-term expansion of knowledge about the universe we inhabit. The universe will not know the difference, but we will. The stars will keep burning. The black holes will keep accreting. The galaxies will keep drifting apart on the current of dark energy. The universe will be exactly what it is, regardless of what any civilization on any planet chooses to do about understanding it. But the understanding is ours, if we choose to pursue it. It is one of the strangest and most unexpected properties of this universe that it produced, in at least one corner of itself, creatures capable of asking what it is. It did not have to do that. The laws of physics that produce stars and black holes and gravitational waves do not require observers. They do not require comprehension. They are indifferent. And yet here we are, comprehending, making sense of it, piece by piece, instrument by instrument, generation by generation. The universe handed us a cosmos and a set of physical laws and a few billion years of biological evolution, and what we did with it was build telescopes and send machines to other worlds, and figure out that the expansion of space is accelerating, and that black holes evaporate, and that the first stars were made of only hydrogen and helium. That is what we did, and we are not done.